In this video, we'll be talking about actuators, what they actually are and how we can actually use them, and some characteristics of different actuators. Firstly, actuators are things that transform energy into motion. And so we have some diagrams there with a number of different types of energy associated with them. Mechanical energy, chemical energy, pneumatic energy, hydraulic, electrical, thermal or combustion related energy. And we transfer that into motion, whether it be rotational motion or linear motion or something a bit more complex where something causes something else to move and causes something else to move in some sort of a coupled environment. But essentially, that's what we're aiming for. We're aiming to actually move something with the energy input that we provide to it. Now we'll have a look at a few different ways we can attach things to these actual motors or actuators in some respect. One common thing that we want to use is flexible couplings. And these fit well into compliance that we'll look at in a few slides' time. But what we often do is it's very difficult to get perfect alignment between our motor and our shaft or our rod or whatever we're trying to drive. And when we've got things like thermal changes and shock and vibration or very small misalignments being introduced into the system, we can damage our system by having something that's non-flexible, something that's very, very stiff. And so if we can introduce a flexible coupling, which we often do, we can tolerate a little bit of misalignment within the system, particularly as we have thermal changes and expansion and contraction that occur at different rates for different materials. There's a few different types of these. You can see the helical slot cut ones where you've essentially got a block of aluminium or something like that and a whole lot of slots cut into it, which allow for a little bit of movement as it can move around. And these have the added benefit of having no backlash. So they're essentially rigid around the direction that we're turning, but then they'll allow us to flex in a couple of degrees off center. We also have spider ones, which are also called jaw flexible couplings. And they've got three different components, and they're essentially a tight fit with some rounded walls to reduce backlash. They're pretty low backlash, but allow a little bit of movement around so that if it's slightly misaligned, we'll still be able to use it and transfer the power across the coupling. These sort of systems will reduce wear for us and also protect our system from stalling and things like that when we're slightly misaligned. So very, very useful to use in a practical sort of sense. Linear actuators are something that's also very handy for us to be able to use and very commonly used in a number of different fields. Essentially what we're trying to do here, when we say linear, we're talking about an actuator here that moves motion in a straight line. There's a few different forms these take. We've got pistons, which are traditionally hydraulic or pneumatic driven or combustion driven as well. And they inject some sort of energy into there, whether it be air-based or whether it be combustion-based or whether it be oil-based, and they can move that piston back and forth. The other type are electric-style ones, and we've got a few different styles of them. We've got lead screw ones with a few different configurations of lead screws, and we've got rack and pinion style ones as well. Those lead screw ones, here's an example with a cutaway section of it. You can see a threaded rod or some sort of an Acme thread that goes through the main section of the thread there. And that's what we're actually turning a captive nut on to actually move our piston shaft in and out. We have a motor down the bottom there, and that motor there is connected either via some gearing like we've got there, or a belt or a worm gear drive sort of system to allow us to control and turn that threaded rod. As we turn that threaded rod, it will push our shaft in and out. Now, our shaft will have some non-rotation elements to it, so that as the thread rod turns, the shaft will just move in and out. It won't turn as well as that thread rod's actually turning. Now we can use a linear potentiometer to provide feedback to tell us where our shaft is at any point in time. We'll often have some cushions around our nut that we're moving back and forward at either end, so we don't hit any of the hard stops very hard. And we can even use feedback from our motor current to actually stop it and tell us that we've reached our endpoint there. Otherwise, we can have some sort of an encoder at either end to tell us we've reached our endpoint as well. And so these are very standard sort of linear actuators used for opening electric doors and things like that, gates and things as well. You can get these up to waterproof standards where your shaft that's being extended in and out will have waterproof bearings and things associated with them as well, bushings there as well. Another technique is the rack and pinion style technique. And here you can see we have a rack and pinion similar to what was often used for our steering sort of systems for cars. Motor there is connected and it's got some sort of a gear on the output shaft of the motor, and that drives back and forth over a rack, moving that rack about in and out. Now, these aren't quite as commonly used. They are used in some industries, but you can imagine as soon as you start getting dust and dirt into that sort of gearbox environment, you're introducing extra wear and extra points of failure. The previous one we looked at seems to be better sealed in that regard, and so you'd be constrained in the sort of environments you'd be able to use this sort of thing. Or you'd be constrained related to the sort of protection that you could offer it as well. One interesting characteristic when we think of our different actuators is that the pneumatic and hydraulic style actuators, where you're pumping in some sort of a fluid or air into something, they're most naturally adapt to in the linear actuator form, where you're moving something in and out through a cylinder. For electric actuators though, you saw our linear actuators before, these are most in their native form in a rotational sort of environment, where we've got magnets that are rotating around an axis. And of course we can connect up shafts and things to that, and connect up rods and create a linear actuator there, but our rotational actuators are typically our motors, and the motors come in many different forms, and we'll look at those in a moment. One other interesting characteristic about actuators is their compliance. And essentially we've got compliant actuators and non-compliant actuators, or actuator mechanisms, we should say. The non-compliant ones are essentially stiff actuators, where once it's in its position, you program it to a position, it will move to that position, or along the trajectory, it will be fixed and it will hold that position regardless of the external force that we apply to it. So we push it, it's not going to move and it will resist our force. Compliant actuators, in contrast to this, will allow deviations from that equilibrium position. So if we apply a little bit of force, it will move a little bit. If we apply more force, it will move even more. And this can take a number of different forms. It can be a passive sort of system with a spring that's there, or it can be an active control system that has feedback associated with it that senses the amount of force that's applied and allows more movement as more force is actually applied. And the idea is when we remove that force, it will move back to its equilibrium position that it was at previously. And sometimes being not stiff, being able to move a little bit, gives a significant advantage, particularly when things aren't perfectly lined up against each other. If they're stiff, they may pull each other apart as they're trying to lock in together. If they have a bit of compliance to them, well, they can mold around and move around each other a little bit. And that will allow us to have something that isn't a perfect fit, actually working quite well together. Now have a look at a brief video showing the difference between compliant and non-compliant actuators and how each of these can be characterized. Here's a little video example where we illustrate the difference between compliant and non-compliant actuators. This actuator on the left is a non-compliant actuator, it's stiff, whereas this one on the right is a compliant actuator, electrically controlled in this case, where we apply force to it and it moves, and when we release the force it moves back to its equilibrium position. We then change this actuator to a medium compliance actuator, and so it will move a bit but not move nearly as much as before. And finally we'll switch it to be a non-compliant actuator, and so it will act a bit like the other one, electrically though, and will resist our motion as much force as we apply to it.